Okay, in this video we're going to check out the beginning here of Chapter 12. This will be a 12.1 Introduction to Limits. And the chapter is titled Limits and an Introduction to Calculus. You're going to see a lot of this stuff if you take Calc next year. We will get into 12-2, Techniques to Evaluate Limits, and also 12.3, the Tangent Line Problem. Okay. Oops. So what we're going to do here in 12.1 in a series of 3 videos, we'll understand the concept of a limit, use the definition of a limit to make estimates of limits, determine whether a limit of a function exists. There's sometimes they do not exist. And we'll use the properties of limits and direct substitution to evaluate limits. So here in example 1, this is kind of a classic problem. We're given a constraint, and then we want to either minimize a bad thing or maximize a good thing. Here we're trying to maximize area, the area of a rectangle. And again, we have this constraint. It says find the dimensions of a rectangle with a perimeter of 24 inches that yields the maximum area. So we've got limited materials, we've got a perimeter of 24 inches, and we want to make a rectangle that has the most area, square, whatever, inches or well, square units. So let's see here. If I draw a rectangle, I'll call this my length and this my width. To find the area, we'll multiply those together. But for perimeter, we got to count all 4 sides. So if the perimeter is 24, we're going to add up 2 W's, and we're going to add up 2 L's. And together, if we add those, that's equal to 24. So let's see here, we've got 2 variables, so let's solve for one variable in terms of the other. The first thing I'm going to do is divide everything by 2. So then I have W plus L equals 12. And just, it doesn't really matter. I'm going to get this L by itself. So L is going to equal 12 minus W. So L is 12 minus W. And now we want to maximize the area of the rectangle. So area equals length times width. Well, we can take out this L and replace it with 12 minus W. So the L disappears, replaced with a quantity, 12 minus W, and we're multiplying that by this W outside. Okay, so let's distribute here. The area of our rectangle will be 12W minus W squared. So now that we've got our area down to a single variable, we can start plopping in some different numbers to see what our area turns out to be. So let's see here. Let's say we make our width 5. If we put 5 into this equation, 12 times 5 is 60, minus 5 squared is 25. If you subtract those, you get 35. So that would be the area 35 square units. Well, let's see what happens if we change our width a little bit to 5.5. Our area goes up to 35.75. Well, let's go up a little bit bigger. Instead of 5.5, let's make it 5.9. And then we get this 35.99. 35.99. If we put 6.0 in there, 6 times 12 minus 6 squared is 36. So here we were getting bigger and bigger. 35, 35.75, 39.99, 36. Let's see what happens if we jump on the other side. Here it was 5.9. Let's jump over to here, 6.1, and we get the output 35.99 again. So this looked like a peak. We were going up, up, up. We hit this peak at 36, and here we started to go down. Let's check 6.5. If that goes into our area equation here, you get 35.75. So it continues to go down. If we put 7 in there, 12 times 7 minus 7 squared is 35. So it did start to go back down. So if we were graphing this, we have a peak here when we were measuring area on the y-axis. We wanted to find maximum area. So here, if we make our width 6, our area is 36. Now, if we think we're done, we're not. Because if we go back and reread the directions, find the dimensions of a rectangle, well, we didn't find the dimensions. Down here, we just found the width. The width we want is 6. width is equal to 6. We want to find the dimension, so we also need the length. Remember, I erased it here. Back when we defined this in one variable, we had length equals 24 minus w. So if we put that 6 in for there, 24 minus 6 would equal 18. Oop, hold on, back up. That L of 24. Remember, I forgot we divided through by 12, or by 2, so that should have been 12 minus W. That's it. Length is 12 minus W. So if we put our width, our 6 in there, 12 minus 6 is 6. So if we have 24 inches of perimeter to work with and we want the most area, a 6 by 6. Actually, it would be a square, not so much a, well, I guess a rectangle is just a square is just a special rectangle. All right. Definition of a limit. Here you're going to see some different notation. When we get into this in calculus, there is plenty of new notation. It says here, if our function f of x becomes arbitrarily close to some unique number L for limit, as our x value gets closer and closer to this c value, from either side, the left or the right, then the limit of our function as x approaches c is equal to L. And this is written like this. The limit, LIM, the limit as x gets close to c, as x approaches c, of our function f of x is equal to some number L. Now I like to tie this in graphically here. This c number is just a special number on our x-axis here. And then here it says x is approaching c. So that just means we're putting x values closer and closer to c into our function. And we can do it from above or below, from the left or the right. This number L is just somewhere a number on the y-axis. If the limit exists, it's going to be some number on the y-axis. So as we're putting values into the function, as we get closer and closer to this c value, there's some value up here on our function. Why is my pen not working? There's some number up here, L, on the y-axis, that as we approach from the left side, we're getting closer and closer to that point. And as we approach from the right side, we're also getting closer and closer to that point. But this c is a number on the x-axis. This L, the limit, if it exists, is a number on the y-axis. So here, example 2, estimating a limit numerically. Use a table to estimate this limit. The limit as x gets close to 2 of this function, 3x minus 2. Okay, now in class we would punch into our TI-89s into the Y editor, Y sub 1. We would type in 3x minus 2. We went to our table settings to make sure it was set to ASK mode. And then we went to our table and we would type in these x values, 1.9, 1.99, and so on. And then get our Y values out of the calculator. Now, unless you have a TI-89 at home and where you're watching this video from, I guess you can't play along, just, write down the values that we get here. So again, we punch this in the Y editor. We want to find out what happens as we approach 2. Well, let's get close to 2. 1.9 is pretty close. That gives us an output of 3.7. If 1.9 is close, 1.99 is closer. If we put that into our function, we get 3.97. Well, if 1.99 is close, 1.999 is even closer. If we put that in, we get 3.997. So as we're approaching here from the left side, from below 2, our y values here seem to be maybe getting closer to some number. Let's try from above. Go above 2. Let's try 2.1. Calculator gives us 4.3. Let's get closer to 2 from above. 2.01 goes in. We get 4.03. Let's get closer, 2.001, and now we're at 4.003. So if we just focus in especially on these numbers right here on either side, we could sort of think about it as an average or what's in the middle. Here, in between 1.999 and 2.001, right in the middle there is 2. So what number do you think is in between 3.997 and 4.003? Well, if we round this one up and if we round this one down, it looks like we would expect to see a 4 there. And in this case, we could just check by putting that 4 into our function. 3 times 4 is 12. Well, if we put 2 in, excuse me, if we put 2 into the function, 2 goes in there. 3 times 2 is 6. 6 minus 2 is 4. So this one we could check just by directly substituting it in. But we can't do that all the time. That's why we're using this idea of a limit. And here's what was happening graphically. So we went to 1.9, 1.9, and we got our output of 3.7. So that was just below that 4.0. And then we got closer, 1.99. So we got even closer in there, and we got even closer to 4. And then we got real close, 1.999, and we were just under that dot at 3.997. When we went to the other side, from the numbers above 2, we were again getting closer and closer as we got closer to that point, closer and closer to 4 on the y-axis. So here, our limit as we approached 2 on the x-axis was equal to 4. That was our number on the y-axis. Okay, let's try these out. The first one is just like example 1. Perimeter is 52. So just follow along, almost identical to example 1 there. And let me give you a little clue. If you don't have a TI-89 at home, as we're checking these, we want a maximum area. When you get your equation down to one function, I'd start maybe by checking x is 11, 12, 13, 14, somewhere 15, and you should be able to find your max in there. Now, when it comes to this second one, if you don't have a TI-89 at home, what we could do, what we're looking at here is we're approaching this 3. So let's just do 2 numbers really, really close. Like I did 2.999, put it in there to see what come out, and then I did 3.001. So instead of, when we did this example, we did a big table with 3 numbers on each side, but really we're just trying to establish what's going on here, on either side of this 3 that we're approaching. So pause the video, give those a try, and start it back up, see if you got them. Okay, just like the first one, we got our length and our width. So our perimeter formula is going to be 2L's plus 2W's equals 52. Divide by 2. Length plus width equals 26. So let's get the W alone. No, let's get the L alone. That's how I did it in my notes. L equals 26 minus W. So area equals length times width. So our length is 26 minus W times width. If we distribute, again, this is very much like example 1. We get our area is 26W minus W squared. And I gave you the hint, start checking, because the W's, we did W was 11. Our area then I got was 165. When I did the width was 12, I got 168, so it got bigger. 13, I got 169, so it got bigger. 14, 168, so I went back down. So here is our peak, our maximum, and that occurred at width 13. So if our width is 13, we had our equation here was 26 minus W was L, so L equals 26 minus 13, or 13. Just like in the example, we found a perfect square. Here our square is 13 by 13. I think in our first example it was 6 by 6. All right, the second one here. Again, I just said check a number on either side of this approach number 3. So we're approaching 3. We want to figure out what's going on at 3. And to check with a short table here, if you put 2.999 into this equation, out pops a negative 2.998. And if we put in a 3.001, out pops a negative 3.002. So as we get real close to either side of 3, what does it look like would be in between these numbers? Well, they're both negative, so the number in between will be a negative. And this number is a little under 3, that's a little over 3, so they would average out to a 3. Negative 3. And in this type of an equation, we can put that directly in. 3 minus 2 times 3. Oops, back there. Yeah, so if we put a 3 in there, 3 minus 6 equals negative 3. That's what we were estimating would happen there. Whoa, there we go. Okay. Again, if you don't have a TI-89 when you're watching this video, just sort of fill in as we go here. It says use a table to estimate this limit numerically. We got x is approaching 0. Our numerator is just an x. And then down here we got a radical x plus 1 and then a minus 1. Well, let's see here. What happens if we put that 0 in there directly? If we directly substitute in the 0, we get a 0 in the numerator. Down here is going to be a root of 0 plus 1. That's a 1 minus 1. Well, the root of 1 is 1, and 1 minus 1 would be 0. So if we try to directly substitute that naughty number 0 in, we get 0 divided by 0. This, I can't remember where this comes up in the book, but they call this indeterminate form. Indeterminate form. From its form, we cannot determine the limit. So in the first couple examples, we could just directly sub it in to see what comes out. Here, not so much. So let's see. Let's approach 0 from either side. Down here in the table, from the negative side, our first one we're going to try out is negative. Oh, let me move this table up here a little bit. Oops. Okay. So if I punch this equation into my y editor, careful with the grouping symbols to make sure that all stays in the denominator. If we punch in this negative 0.01, our calculator gives us out 1.99499. If we get closer to 0, we tuck another 0 in there between the decimal and the 1. Our calculator spits out, I'm going to write it down here, 1.9995. If we put in this negative, even smaller number, add another 0 in there, we get 1.499995. Okay, so as we're getting closer and closer to 0 here from the left side, it looks like we're approaching some number here from the left side. Let's go above 0. Here's some positive numbers. Way out here at 0.01, our calculator would give us a 2.0049. If we put another 0 in there, gets a little smaller, 0.001. We get 2.0005. And if we put in this negative or the positive 0.0001, we get 2 point. Now there's 4 zeros in there. 2.00005. So again, if we just focus in right here on either side of that 0, what's in between 1.99995 and 2.0005? If we round each of them off, it looks like there's going to be a 2 in there. Now, we found that from a table. Let's see if we could reinforce that with a graph. So here, if we went to the graph feature on our TI-89, it's going to look something like this, but when we tried to put 0 in, we got 0 divided by 0, so our graph is undefined. There's a hole in the graph right at when our x value is 0. But we put some numbers from the left side in here, negative 0.01, 0.001, negative 0.0001, and we got some numbers here just underneath 2. When we come in from above, from a few positive numbers, 0.01, 0.001, 0.0001, we got a few numbers up here that were above 2. So to the left, we were under 2. To the right, we were above 2. So that means what's going on right at that hole, that limit is equal to 2. A lot of times, the limit of a function is the height of the hole in the graph. If we had another function where maybe we had a hole here, as we approached that hole, that limit would be 3. A lot of times, the limit of a function is the height of the hole in the graph, that height on the y-axis. And here's our last example for this video. We've got this one, just a rational function here, polynomial on the top and the bottom. Let's see, if we're approaching 1, if we put that 1 in the numerator, we get 1 minus 1 plus 1 minus 1, and that's going to equal 0. If I put the 1 in the denominator, 1 minus 1 is 0. So again, we run into that indeterminate form, 0 divided by 0. So we can't plug in 1 directly. Let's plug in some values that are close and see if we can figure out what's going on the y-axis. So here we're approaching 1. To the left of 1 is 0.9. That gives us a y value of 1.81. Let's get closer, 0.99. That's y value is 1.9801. And if we put in 0.999, we get 1.998. Again, we can't plug in 1 directly. We get that indeterminate form. So let's now, let's hop over here to the right side. 1.1, that's pretty close to 1, but our y value would be 2.21. 2.21. If we slide a 0 in there, make this number get closer to 1, our y value is 2.0201. And if we get even closer to 1, 1.001, we get 2.002. 2.002. Again, focus in real close to that naughty number of 1. We got a y value here a little under 2. This y value is a little over 2. So it looks like our limit as x approaches 1 of our function, f of x, is equal to 2. Oops. Let's look at the graph on this one also. Graphical solution. Oops. Ooh, and this is a good time to point out maybe a little flaw on the TI-89. So if we graph that here, it's going to look like this. We could use the trace feature. You know, we could try to get really close to 1 on the x value here and see what our y value is doing. But on our TI-89's display, you're not going to be able to see the hole in the graph. It would be impossible. You know, we'd have to maybe zoom in a bunch of times and change a few settings. Okay. Here's a couple for you to try, couple checkpoints. Again, if you don't have a TI-89 at home, here we're approaching, that shouldn't use white ink, there we go. Here we're approaching positive 1. So 1 is the number that we're investigating. Just try 0.999 or 0.99 might be enough to get it to work. Do 999. And then on the other side of 1 would be 1.001. Down for the second one here, our approach number, the number that we're investigating, is 2. What is going on with my pen? It's getting a little glitchy here. Okay, again, we're, oh, come on. Due to technical difficulties. Okay, again, our number, oh, and here we go again. The number here is 2 that we're approaching, so just try out 1.99 and 2.01. Those are numbers real close to 2, and we should be able to figure out what's going on with that second one. So pause the video, try to find those limits, and start it back up, see if you got them right. Okay, up here. Oh, come on. We're approaching 1, and I used, well, I did, yeah, let's just do it to 0.999. That should be enough. 0.9. Let's try this again. Our approach number here is 1. So I put in 0.999, and I got out a 0.2. And if you put in 1.001, you'd also get out a 0.2. And I guess this one, we'd have to go a little bit farther. If we had another one in there, oh no, I guess that, excuse me, the 0.999, that should have gave me 0.2004. And then the other one, 1.001, that would have been 0.19996. That's it. So here we're a little bit above point 0.2 with a little bit more, and here we're just below point 0.2. So that would be point 0.2, or if you like fractions, 1/5. And the second one, our number of approach was 2. And I did to 4 places here, 1.9999. That gave me a 6.9996, and 2.0001 gave me a number 7.0004. Let me guess here, if you did one less 9 on there, this 6 probably moved over a spot. And if you did one less 0 in there, this 4 probably moved over a spot. Either way, if you look at it here, we're just a little bit under 7. If we round this up, we get to 7. Here, we're at a little bit over 7, so if we round this down, we get to 7. So it sure looks like that limit is going to be 7. The homework for this one is just 4 questions. This is on WebAssign. If you are having any issues on the WebAssign site or on computer in general, you can always go to this page in the textbook and do these 4 problems.